Module 8, Lecture A, Distances, Kernels. By the end of this lecture, you will be able to compute pairwise distances and similarities for small datasets, compare common distance metrics and kernel functions visually and numerically, and use pre-computed distance or kernel matrices with compatible estimators. Distance metrics. Pairwise distance matrix. A pairwise distance matrix summarizes how different each item in a small dataset is from every other item. Rows and columns represent the items, and each entry gives the distance between a pair. The diagonal is 0 because an item has no distance from itself, and the matrix is symmetric because the distance is the same in both directions. This makes it easier to see relationships and patterns that may not be clear in the raw data. A pairwise distance matrix compares every item in a dataset with every other item using a numerical distance. For houses, this could reflect differences in features such as size, bedrooms, or distance from the city center, where smaller values mean greater similarity. The same idea applies in fields like biology and marketing, and it supports methods such as clustering and nearest neighbor analysis. When building a pairwise distance matrix, prepare the data carefully because feature scale and meaning strongly affect the results. Standardize or transform features when needed, decide whether they should have equal weight, and represent categorical data appropriately. For small datasets, check a few distances by hand to see if they match expectations. If similar items look far apart or different items look close, revisit the feature scaling, feature selection, or distance metric. Python code, pairwise distance matrix. This example creates a small distance matrix that compares each observation with every other observation. A heat map then makes it easy to identify which pairs are closest and which are farthest apart. We import key Python libraries to prepare and analyze the house feature data. NumPy supports numerical work, Pandas organizes the data in tables, and Matplotlib helps visualize the distance matrix as a heat map. Scikit-Learn provides tools to standardize the features and calculate Euclidean distances between each pair of houses, so all features contribute fairly to the comparison. We create a small Pandas data table for 4 houses, labeled A through D. Each row represents one house, and the table stores 3 numeric features: area, number of bedrooms, and distance from the city center. The house labels are used as the index, so each house can be referenced easily. We standardize the house data, so no single feature, such as area, has too much influence on distance calculations. A standard scalar is used to transform each feature, so it has a mean of 0 and a standard deviation of 1, putting all features on a comparable scale. We use Scikit-Learn's pairwise distances function to calculate Euclidean distances between all scaled house records. The result is a distance matrix, showing how similar or different each pair of houses is based on their standardized features. These distances are then placed in a labeled Pandas data frame and rounded to 2 decimal places for easier interpretation. We validate the distance matrix by checking 2 key properties. First, its diagonal should be all zeros, meaning each house has 0 distance to itself. Second, the matrix should be symmetric, so the distance from one house to another is the same in both directions. These checks can be done by comparing the diagonal to 0 and the matrix to its transpose using NumPy's all-close function. After standardizing the features, we display the pairwise Euclidean distance matrix for the houses. We then confirm 2 key properties. Each house has 0 distance to itself, shown by zeros on the diagonal, and the matrix is symmetric, meaning the distance from one house to another is the same in both directions. To find the closest pair of houses, we first copy the distance matrix, so the original data stays unchanged. We then set the diagonal values to infinity, preventing any house from being matched with itself. Finally, we locate the smallest remaining distance using NumPy's minimum value indexing tools, which gives the positions of the closest two different houses. The code finds the two houses that are closest together by using the stored location of the smallest non-diagonal value in the distance matrix. It then retrieves their names, looks up the distance between them, and prints a short result showing the closest pair and their distance rounded to 2 decimal places. Create a matplotlib figure and axis with a 5 by 4 inch canvas. Then display the distance values as a heat map using the image display function. A blue color map shows smaller and larger distances with different shades, making the values easy to compare visually. The code sets both the horizontal and vertical tick positions to match the number of houses, then labels those ticks with the house names. This makes the heat map easier to read by clearly showing which row and column correspond to each house, so distances between specific houses can be identified. The heat map is labeled so both rows and columns represent houses, making it clear that each cell compares one house with another. The title identifies it as a pairwise distance matrix, and the color bar provides a scale for interpreting the Euclidean distances between houses based on their features. The code goes through the distance matrix and adds a centered label to each heat map cell. Each label shows the distance between the corresponding houses, rounded to 2 decimal places, so the values are easy to read and compare. Adjusting the layout makes sure the plot elements fit cleanly without overlapping or being cut off. Then, displaying the plot shows the heat map, so you can visually examine the pairwise distance matrix. This script compares 4 houses using their area, number of bedrooms, and distance from the city center. It first standardizes the features, then calculates pairwise Euclidean distances in a symmetric distance matrix, where each house has 0 distance from itself. It identifies the closest pair of different houses and displays the results in a heat map, making the nearest and farthest pairs easy to compare. Euclidean, Manhattan. Euclidean and Manhattan distances measure how far apart data points are. Euclidean distance represents the straight line separation between points and is useful for continuous features, such as comparing observations in a shared space. Calculating distances for every pair of observations creates a distance matrix, which summarizes how similar or different the data points are. Manhattan distance measures how far 2 observations are by adding the absolute differences across their features, like moving along a city grid instead of diagonally. It is useful when features represent independent amounts, such as counts or resource use, because it captures the total change needed to move from one observation to another. Unlike Euclidean distance, a large difference in one feature is not smoothed out by smaller differences elsewhere, so it can produce a different view of which observations are close. Choose Euclidean or Manhattan distance based on how your data defines similarity. Euclidean distance works best for continuous features on similar scales, where geometric closeness matters, while Manhattan distance fits cases where differences accumulate across dimensions. Always scale features carefully, because large-valued variables can dominate the result. For small datasets, comparing both metrics can show how they change nearest neighbors and clusters. Python code. Euclidean Manhattan. This section compares 2 common distance metrics and shows how they can produce different views of closeness. Small point sets make the pairwise distances easy to see, while distance matrices summarize the resulting patterns. We import NumPy for efficient numerical work with arrays, and pandas for handling and analyzing tabular data. We also use the pairwise distances function from Scikit-Learn to measure how close or far apart data points are, using metrics such as Euclidean or Manhattan distance. We define 3 two-dimensional points using a NumPy array, with each row holding 1 point's 2 numeric features. The points are 0, 0, 3, 4, and 5, 1. We also assign labels A through C, so the points can be identified clearly when distance matrices are created. The code first verifies that the points data has 3 rows and 2 columns, meaning 3 observations with 2 numeric features each. If the data does not match this expected shape, it raises an error. This check helps prevent problems later, because the distance calculations rely on that exact structure. We compare points by computing pairwise distance matrices with Scikit-Learn. Using the Euclidean metric gives the straight line distance between each pair, while the Manhattan metric gives the sum of the absolute coordinate differences. Together, these matrices show how the same points relate under different distance measures. Pandas data frames are used to organize both the Euclidean and Manhattan distance matrices. By labeling the rows and columns with point identifiers, the distances between each pair of points become easier to read and compare in a structured format. The output first identifies points A, B, and C with their coordinates to give context. It then shows both the Euclidean and Manhattan distance matrices, rounded to 2 decimal places, so learners can easily compare how each metric measures closeness between the same points. This script compares Euclidean and Manhattan distances for 3 two-feature points. It verifies the data shape, computes pairwise distances with both metrics, and prints rounded distance matrices for easy comparison. Euclidean distance measures straight-line closeness, while Manhattan distance adds the absolute differences across dimensions, so the 2 metrics can show different patterns of proximity. Custom distance metrics. Custom distance metrics are useful when standard measures like Euclidean or Manhattan distance do not reflect what similarity means for your data. They let you decide which features matter most, such as rent and commute time for apartments, or symptoms and test results for patients. By embedding domain knowledge into the distance calculation, custom metrics can produce more meaningful comparisons, especially in small datasets where you can inspect how the chosen metric changes the distance matrix. A custom distance metric should reflect which features matter for judging similarity and how strongly each one should count. Important features can be weighted more, while noisy or less relevant ones can be reduced. The right weights depend on the task, such as forming teams versus estimating salary. Custom metrics can also compare mixed data types by using suitable rules for each feature, such as price differences, brand matches, or dietary categories. When designing a custom distance metric, make it consistent, interpretable, and appropriate for the data context. Test it on small examples to confirm that similar items have small distances and different items have large distances. Also ensure it meets any algorithm requirements, such as non-negative distances and zero distance for identical points. And document the metric clearly so others can understand the resulting distance matrix. Python code custom distance metrics. This example shows how to create a custom distance metric by using feature weights to define what similarity means. It then compares the results from standard distances with the custom weighted distance. We import NumPy for efficient numerical work with arrays, pandas for organizing and analyzing data, and Scikit-Learn's pairwise distance tools to measure distances between data points. Together, these libraries provide the basic setup for data handling and distance calculations in the script. A pandas data frame is created to organize apartment data, with each row representing one apartment, labeled A through D. The columns store key numeric features, including monthly rent, commute time, number of bedrooms, and floor number. This structure makes the apartment information easy to analyze and manipulate in pandas. Create a copy of the apartment's data so the original stays unchanged. Then, rescale key features before comparing distances. Rent values are divided by 100, and commute times are divided by 10, so neither feature dominates the calculation. This puts the attributes on more comparable scales for a balanced comparison. Feature weights are used to control how much each apartment attribute affects the distance calculation. In this setup, bedrooms matter most, followed by rent and commute time, while floor number has only a small effect. These weights let us measure apartment similarity based on the factors that are most important for the analysis. This function measures the weighted Manhattan distance between two data rows. It compares matching values, takes their absolute differences, applies feature weights, and adds the results together. The weights let more important features have a larger effect on the final distance. We compare apartments by calculating pairwise distances between their scaled features. First, we use the standard Manhattan distance, which adds the absolute feature differences. Then we use a weighted Manhattan distance, which gives some features more influence than others. Both methods produce distance matrices that show how similar or different each apartment is from every other one. We first define the required distance matrix size, so it has one row and one column for each apartment. This makes the matrix square, which is necessary for representing pairwise distances between all apartments. If the provided matrix does not match that size, an error is raised to signal that the distance data is invalid. We create two labeled pandas series showing apartment A's distances to the other apartments, one using the standard distance matrix and one using the custom distance matrix. These are combined into a data frame so the two distance measures can be compared side by side, with values rounded to 2 decimal places for readability. The output first announces that it will show distances from apartment A to the other apartments, then prints the comparison data in a readable string format. This lets the standard and custom distance metrics be viewed side by side. Finally, it finds the closest apartment to A by ignoring A's distance to itself and selecting the smallest custom distance, then prints that apartment as the result. This script compares apartment similarity using both standard and custom distance measures. It first scales rent and commute so they do not dominate the results, then applies a weighted Manhattan distance that gives rent and commute more importance than floor number. After computing and checking the distance matrix, it shows which apartments are closest to apartment A under the custom metric. The main idea is that feature weighting can change how similarity is judged in a dataset. Similarity kernels. Cosine similarity. Cosine similarity measures how alike two data points are by comparing the direction of their feature vectors rather than their size. This is useful when the pattern of features matters more than magnitude, such as comparing documents of different lengths that use similar word proportions. Vectors pointing in the same direction are highly similar. Right angles suggest little relation, and opposite directions indicate dissimilarity when negative values are possible. Cosine similarity compares data points by the direction of their feature vectors, rather than their absolute distance. Values close to 1 mean the points have similar patterns, while values near 0 mean they are poorly aligned. This is useful when the proportions or shape of the data matter more than the overall size, such as customers buying different amounts but in similar category patterns. Cosine similarity measures how similar observations are in direction, helping reveal shared patterns even when their overall sizes differ. It is useful in areas like text analysis, gene expression comparison, and recommendation systems. However, it can miss important differences in magnitude, such as symptom severity, so it works best when pattern direction matters and should be compared with other metrics.
Python code.
Cosine similarity. This example compares cosine similarity values to show that similarity depends more on vector direction than on vector length. The heat map highlights which items share similar patterns. We import key Python libraries for data analysis and visualization. NumPy for efficient numerical work, pandas for handling tabular data, matplotlib and Seaborn for creating visualizations, and Scikit-Learn's cosine similarity function to measure how similar vectors are based on their direction rather than their size. We define customer names that describe different buying patterns, then store their purchase data in a NumPy array. Each row represents one customer, each column represents an item category, and each number shows how many items were bought. This structure makes it easy to compare purchasing behavior across customers. We compute the length of each customer's purchase row to measure the size of their purchase pattern. Then we check whether any row has zero length, which would mean that customer has no purchases, and cosine similarity would be undefined. If any row is entirely zero, we raise an error to ensure every customer has at least one non-zero feature. We use Scikit-Learn's cosine similarity function to compare customers' purchase patterns by measuring how closely their purchase vectors point in the same direction, regardless of size. The resulting similarity matrix is then converted into a pandas data frame, with customer names as both rows and columns, making the relationships easier to read. We compare customers A and B using two measures. Euclidean distance shows how different their purchase amounts are by measuring the gap between their purchase patterns. Cosine similarity shows how closely their purchase directions align, regardless of total volume. Together, these metrics reveal both magnitude and direction in customer behavior. We compare customers A and B using two measures, cosine similarity and Euclidean distance, each rounded to 3 decimal places. Cosine similarity shows that their purchase patterns have similar proportions, while Euclidean distance shows that their total purchase amounts differ. This highlights that cosine similarity focuses on direction, not scale. A heat map is created to visualize cosine similarity between customers. The plot is sized for readability, and the Seaborn heat map function displays the similarity table with values shown directly on the chart. A Veritas color scale from 0 to 1 represents the full similarity range, and the annotations are rounded to 2 decimal places for clarity. The plot is titled to show that the heat map represents a cosine similarity kernel for customer purchase patterns. Both axes are labeled as customers, so each row and column corresponds to a customer being compared. The layout is adjusted to keep the figure neat, and the plot is then displayed for visual interpretation. This script compares customer purchase patterns using cosine similarity, which measures how alike the proportions of purchases are across categories, regardless of total spending. It checks that purchase data is valid, then shows that customers with similar ratios can appear highly similar even if their purchase volumes differ. Euclidean distance is also calculated to show how a magnitude-based measure can give a different view. A heat map summarizes the cosine similarities, making it easier to see which customers have similar buying behavior by pattern rather than quantity. Linear polynomial kernel. A linear kernel measures similarity by checking how strongly two feature vectors align in both direction and size. Points are considered more similar when their features tend to be large or small together, reflecting shared patterns across observations. Unlike distance measures, it focuses on alignment rather than separation, making it useful for finding broad co-occurrence patterns in data. A polynomial kernel extends the linear kernel by measuring not only individual features, but also combinations of features. This lets it capture interactions, such as when two housing attributes together make homes more similar. As a result, It can model more complex relationships without manually creating new combined features, often producing clearer similarity contrasts and sharper clusters when interactions matter. When choosing between linear and polynomial kernels, first consider feature scaling, since large values can dominate unless the data is standardized. A linear kernel is easier to interpret and works well for direct feature relationships, while a polynomial kernel can capture more complex feature interactions but is harder to explain. In general, use a linear kernel for simpler patterns and a polynomial kernel when combinations of features are important. Python code, linear polynomial kernel. Linear and polynomial kernels measure similarity in different ways, with the polynomial kernel often creating stronger contrast between data points. Scaling is important because it prevents features with larger values from dominating the similarity calculation. A heat map can make this contrast easier to notice by showing the polynomial kernel's stronger separation. We import key Python tools for working with data and visualizing results. NumPy supports numerical operations and arrays, while Matplotlib helps create plots and heat maps. From Scikit-Learn, we use linear and polynomial kernel functions to measure similarities between data points, and standard scalar to standardize features so they contribute more evenly to those calculations. We define a small set of customers labeled A through E, then store their purchase data in a NumPy array. Each row represents one customer, and each column represents a product category. The purchase values are stored as floating point numbers to support accurate calculations later. Before computing pairwise similarities, the code verifies that the purchase data has 5 rows and 2 columns. This confirms the expected structure of 5 customers with 2 numeric features each. If the shape is wrong, it raises an error, so later calculations do not run on invalid data. We use Scikit-Learn standard scalar to put both product categories on the same scale before comparing them. Applying the scalar to the purchase data standardizes each feature, so it has a mean of 0 and a standard deviation of 1. This helps ensure that no single category has too much influence on the similarity calculations. The code compares customers by calculating linear similarity scores from their scaled purchase data. It uses Scikit-Learn's linear kernel, which measures the dot product between customer feature vectors. This gives a simple way to see how closely customers' purchase patterns align. Polynomial similarity scores are calculated with a polynomial kernel using scaled purchase data, so product categories are weighted evenly. With degree 2, the method captures quadratic feature interactions, making the comparison richer than a linear similarity measure. The chosen settings also add flexibility and control how strongly individual features influence the final similarity score. We compare customer similarity by reading scores from the linear and polynomial similarity matrices. For customers A and B, the linear score shows similarity based on scaled purchase data, while the polynomial score also captures feature interactions. We then repeat the comparison for customers A and E, a pair expected to be less similar, and round each score to 2 decimal places for easier interpretation. We visualize the polynomial similarity matrix by creating a clear plot and displaying the similarity scores as an image. A color map is applied to make differences in the scores easier to see, helping reveal patterns and contrasts in the matrix. The plot is titled Polynomial Kernel Similarity and uses both axes to represent customers. This makes clear that the heat map is a customer-by-customer matrix showing similarities calculated with a polynomial kernel. Set the tick positions on both axes to match the number of customers, so each customer has a place on the heat map. Then, label those ticks with the customer names instead of numbers. This makes both axes clear and helps the heat map show customer relationships in an easy-to-read way. The code adds a color bar to show the range of similarity scores in the polynomial kernel heat map, making the color intensities easier to interpret. It then adjusts the layout to prevent overlap, and displays the plot so the amplified similarity blocks among customers can be analyzed visually. This script compares linear and polynomial kernel similarity on standardized customer purchase data, so each product category contributes equally. Linear similarity measures direct feature alignment, while the degree 2 polynomial kernel gives more weight to feature interactions and can amplify differences between customers. By comparing similar and different customer pairs and showing a heat map of the polynomial similarity matrix, the script illustrates how polynomial kernels can reveal stronger and more nuanced similarity patterns. RBF Laplacian kernels. RBF and Laplacian kernels turn distance into a measure of similarity, so nearby observations influence each other more than distant ones. This helps model nonlinear relationships, such as similar homes in housing data or similar patients in medical data. Overall, these kernels create a smooth similarity pattern that is strongest for close points and fades as distance increases. The RBF and Laplacian kernels both measure similarity by giving more weight to nearby points and less to distant ones. The RBF kernel decreases smoothly with distance, while the Laplacian kernel falls off more sharply depending on its scale setting. This difference affects how models define neighborhoods, such as grouping gradually changing images or separating documents based on finer differences. For RBF and Laplacian kernels, the scale parameter controls how quickly similarity falls as distance increases. If the scale is too small, points look isolated. If it is too large, most points look overly similar and important patterns can disappear. Comparing kernel matrices can help judge whether the kernel is capturing local or global structure. These kernels are useful for nonlinear modeling, but they work well only when their shape and scale match the data. Python code, RBF Laplacian kernels. RBF and Laplacian kernels both turn distances into similarity scores, but they decrease with distance in different ways. The scale setting controls how quickly similarity falls, shaping how strongly nearby and farther points are treated as related. This setup imports key Python tools for numerical work, visualization, and similarity measurement. NumPy supports efficient array and math operations, while Matplotlib's plotting module is used to create visualizations. From Scikit-Learn, it also imports the radial basis function kernel and the Laplacian kernel, which both measure similarity between data points using different distance-based methods. We create a smooth set of distances from 0 to 4 using 81 evenly spaced values. These distances are reshaped into a column format so they work with later kernel calculations. A reference point at the origin is then defined, allowing similarities to be measured from that point using different kernel methods. Two gamma settings control how quickly similarity drops as distance increases. A smaller value of 0.5 makes similarity decay more slowly, while a larger value of 2.0 makes it decay faster. These settings adjust the sensitivity of similarity calculations in the RBF and Laplacian kernels. We compute radial basis function similarity using squared Euclidean distance between the points and a reference. A small gamma value makes similarity decrease more slowly with distance, while a larger gamma makes it drop faster. Flattening each result into a one-dimensional array makes it easier to compare how gamma changes the similarity pattern. The code uses the Laplacian kernel to measure similarity between points and a reference based on absolute distance. It computes scores with a smaller gamma value and then with a larger one, flattening each result for comparison. This shows how gamma controls how quickly similarity decreases as distance grows. The code verifies that the radial basis function kernel output has the same shape as the distance grid. This ensures each similarity score lines up with its corresponding distance value. If the shapes do not match, it raises an error to prevent unreliable analysis or visualization. The code prints similarity scores for RBF and Laplacian kernels to compare how they behave at different distances and gamma values. At 0 distance, both kernels give the maximum similarity score of 1. It then reports the scores at distance 2 for gamma values of 0.5 and 2, showing how the kernel type and gamma setting affect how quickly similarity decreases. A plotting canvas is created. Then 4 similarity curves are drawn against distance for comparison. The graph includes radial basis function and Laplacian similarities with gamma values of 0.5 and 2.0. Each curve is labeled, so the legend can clearly distinguish the similarity type and gamma setting. The plot is formatted to clearly show how RBF and Laplacian kernel similarity scores decay with distance from a reference point. It includes a descriptive title, labeled axes for distance and similarity, a legend to distinguish the curves, and a lightly transparent grid to make the graph easier to read. The plot is displayed, showing the kernel similarity curves that were set up earlier. This lets you compare how the RBF and Laplacian kernels change across distances for different gamma values. This script compares how radial basis function and Laplacian kernels convert distance into similarity. It tests distances from 0 to 4 with gamma values of 0.5 and 2, showing that the radial basis function kernel decays based on squared distance, while the Laplacian kernel uses absolute distance. It prints example similarities at distance 2 and plots the curves, making clear that larger gamma values cause similarity to drop more quickly. Special kernels. Chi-squared kernel. The chi-squared kernel measures similarity for count data and non-negative histograms, such as color distributions or topic proportions. It focuses on relative differences between categories, rather than treating every raw difference the same. This makes it useful when the overall shape of a distribution matters more than the absolute size of its values. With a chi-squared kernel, compatible estimators learn from a similarity matrix rather than the original feature vectors. This matrix compares each pair of observations using the chi-squared measure, giving the algorithm a kernel-based view of the data. For histogram data, this can produce decision boundaries that better reflect meaningful differences in distributions. So the choice of kernel can strongly affect model behavior. The chi-squared kernel is useful only when the data fits its assumptions. It works best with non-negative features that represent comparable categories, and negative or mixed measurements should be transformed before use. Proper normalization is also important, so the kernel compares meaningful distributions rather than irrelevant scale differences. When matched to the data correctly, it can capture useful distributional patterns. Python code. Chi-squared kernel. This example creates a chi-squared kernel matrix for histogram data. The histograms must be non-negative and comparable, and the resulting similarity matrix is used with a pre-computed support vector machine. The script imports key tools for numerical work, visualization, similarity measurement, and model evaluation. NumPy supports efficient array operations. Matplotlib helps create plots. The chi-squared kernel computes similarity between histogram samples, and the train test split function divides data into training and testing sets for fair evaluation. The script imports the support vector classifier from Scikit-Learn to build a model using a pre-computed kernel matrix. It also imports the accuracy score function to compare predicted labels with true labels and evaluate performance. Finally, it imports Scikit-Learn itself, so the script can check the library version for compatibility and reproducibility. We create a two-dimensional NumPy array, where each row is a small, normalized histogram. Each histogram is a non-negative probability distribution, with values across bins that add up to 1. This format makes the data suitable for comparing histogram similarity using a chi-squared kernel in a machine learning setting. We use a NumPy array to store the labels for the histogram samples. Each label gives the sample's category. 0 means the histogram is red heavy, and 1 means it is blue heavy. These labels provide the ground truth needed to train the model and evaluate its predictions. The code first checks whether the input data contains any negative values, because chi-squared kernels require all features to be non-negative. If a negative value is found, it raises an error explaining the requirement. This prevents invalid data from being used in later computations. We first create sample indices so each data point can be tracked during splitting. Then, Scikit-Learn's train-test split is used to divide them into training and testing sets, with 1/3 reserved for testing. A fixed random state makes the split reproducible, and stratifying by the labels keeps class proportions balanced in both sets. We split the original dataset into training and test subsets using the chosen indices, and assign the matching labels to each subset. The training data is used to build the model, while the separate test data is used to evaluate how well it performs on unseen examples. This separation helps check whether the model can generalize beyond the data it learned from. We set gamma to 2.0 to control how quickly similarity drops as samples become farther apart. Using this value, we compute a chi-squared kernel matrix for the training data by comparing all training samples with each other. We also compute a test kernel matrix by comparing each test sample with the training samples, producing the similarities needed for prediction. We create a support vector machine using Scikit-Learn and set it to use a pre-computed kernel, so it learns from a similarity matrix rather than raw features. The model is then trained with the training kernel matrix and its labels, allowing it to find patterns based on those similarities. The model predicts test labels using a pre-computed kernel matrix, which represents similarities between test samples and training samples instead of the original features. Its performance is then measured by comparing the predicted labels with the true test labels. The accuracy score shows the proportion of test samples classified correctly. The output checks the Scikit-Learn version for reproducibility, shows the size of the training kernel matrix, and reports the test accuracy of a support vector machine using a pre-computed chi-squared kernel. Together, these values confirm the setup, describe the input similarity data, and give a quick measure of performance on unseen data. We create a matplotlib figure and axis, then display the training kernel matrix as an image. The visualization uses the Viridis color map, with values scaled from 0 to 1. This gives a quick view of pairwise similarities between training samples, helping interpret how the kernel behaves. The plot is titled Pre-computed chi-squared kernel to show that it visualizes a kernel similarity matrix. Both axes are labeled as training sample indices, indicating pairwise comparisons between training samples. A color bar is included to explain how the colors correspond to similarity values. Finally, we use matplotlib's show function to display the plot. This opens the visualization of the training pairwise similarities, making it possible to inspect the chi-squared kernel matrix. This script builds a chi-squared kernel for non-negative histogram data, such as color distributions, and uses it to train a support vector machine. The data is split into balanced training and test sets, and the model learns from pre-computed similarity values rather than the raw histogram features. The output reports the Scikit-Learn version, the training kernel shape, and the test accuracy, while a heat map shows how the kernel captures similarities among training samples. Pre-computed matrices. Pre-computed matrices let you give an estimator a ready-made square matrix of relationships between observations, instead of having it compute them itself. The matrix may represent distances, showing how far observations are from each other, or similarities, as in a kernel matrix. This is useful for non-numerical data, such as DNA sequences or documents, where domain-specific measures can be turned into pairwise relationships for machine learning. When using a pre-computed matrix, make sure it matches what the estimator expects. Some methods use distances, where smaller values mean observations are closer, while others use kernels, where larger values mean greater similarity. The matrix must also be in the same order as the training labels or examples, because any mismatch can lead to incorrect learning. This applies whether the data represents patients, customers, images, or other observations. Pre-computed matrices are useful because they store relationships among training observations, but they must be applied consistently to new data. If a model uses a custom similarity measure, future items need to be compared in the same way. In cross-validation, each fold also needs matrices with the correct size and ordering. These matrices work best when they reflect meaningful structure in the problem and remain compatible with the estimator. Python code, pre-computed matrices. This example shows how pre-computed matrices can be used with a small classifier. Before training, distances are converted into similarities so the model can use them effectively. The results then compare performance with the correct alignment against a shuffled alignment. We import NumPy for efficient numerical work and use Scikit-Learn for the machine learning tools needed in this example. These include tools to create synthetic blob data, split it into training and testing sets, measure prediction accuracy, and compute pairwise distances that can be converted into similarities. The model is a support vector classifier trained with pre-computed similarity matrices rather than raw features, so we can study how data alignment affects classification performance. A small two-class dataset is created using Scikit-Learn's makeBlobs function. It generates 40 data points grouped around two centers, with enough spread to create some overlap while keeping the classes distinct. A fixed random state makes the results reproducible, producing both the data features and their class labels for studying pairwise relationships. We first divide the dataset into training and testing sets, using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, while stratification keeps the class proportions consistent with the original dataset. A fixed random state makes the split reproducible, which is important because later comparisons depend on the exact training and test rows. We set the similarity spread parameter to 0.2, then compute distances between every pair of training feature vectors. These distances are converted into similarities with an RBF kernel by applying an exponential transformation to the negative scaled squared distances. The result is a kernel matrix where higher values mean samples are more similar, ready for model training. Before training with a pre-computed kernel, the training kernel matrix is checked to make sure it is square and matches the number of training labels. If it does not align correctly, an error is raised. This prevents label and matrix mismatches that could cause problems during model training. We create a support vector machine with Scikit-Learn support vector classifier and use a pre-computed kernel. This means the model learns from a similarity matrix rather than raw feature values. Training then uses the kernel matrix and labels to capture relationships between the data points. To predict test labels, we compare each test sample with the training samples by computing their pairwise distances. These distances are then converted into similarity scores using an exponential transformation based on gamma and the squared distance. The resulting test kernel matrix captures how similar each test sample is to the training data, and the trained model uses it to make predictions. This example shows why labels must stay aligned with a pre-computed kernel matrix. By reversing the training labels before fitting a support vector machine, the labels no longer match the corresponding training examples in the kernel matrix. Predictions made from this incorrectly trained model are likely to be poor, demonstrating that correct label order is essential for reliable performance. The process checks the Scikit-Learn version for reproducibility, then verifies that the training and test kernel matrices have the expected shapes. It measures model accuracy using correctly aligned labels to show normal performance, then repeats the accuracy calculation with shuffled labels to demonstrate how label misalignment can reduce performance. This script shows how to train a small support vector machine using a pre-computed kernel. It creates a two-class dataset, converts distances between training samples into an RBF similarity matrix, and uses that matrix for training and prediction. The main lesson is that labels must stay in the same order as the kernel matrix rows. When labels are aligned, accuracy is higher, but when they are shuffled, performance drops sharply. Kernel limitations. Kernel methods let models work with similarities rather than raw features, but the similarity matrix must be a valid kernel. It needs to be symmetric and represent observations in a consistent inner product structure. If a pre-computed similarity matrix does not meet these conditions, models such as support vector machines can produce errors or unstable results. For this reason, pre-computed kernels require careful validation before use. Kernel matrices grow quickly because they store similarities between every pair of observations, making them expensive to compute and store for large datasets. Adding new data is also costly, since similarities must be recalculated against existing entries. For this reason, kernel methods are most practical for moderate-sized datasets, where the chosen similarity measure provides enough value to justify the computational cost. Choosing a kernel matters because it determines what patterns a model can learn and how its results can be understood. Different kernels make different assumptions about similarity, and a poor match can cause overfitting or weak performance on new data. Because kernel models depend on pairwise similarities, it can also be hard to identify which features drive predictions. This makes it important to validate the kernel, check estimator compatibility, and test performance on fresh data. In this lecture, you learned to compute pairwise distances and similarities for small datasets, compare common distance metrics and kernel functions visually and numerically, and use pre-computed distance or kernel matrices with compatible estimators. In the next lecture, Lecture B, we will go over kernel approximation.
Thank you for your attention. See you all in the next lecture.